Our story begins in the late summer of 1977, a time when the world was captivated by the promise of space exploration. In the midst of the Cold War, as technology leapt forward and imagination soared, NASA prepared for a mission unlike any before. That year, humanity launched two remarkable emissaries, Voyager 1 and Voyager 2, destined to journey farther than any spacecraft before them. Their mission? To explore the mysterious gas giants and send back knowledge that would forever change our understanding of the solar system. Voyager 2, in particular, embarked on a unique and ambitious path, flying past all four giant planets, Jupiter, Saturn, Uranus, and Neptune, a grand tour made possible by a rare planetary alignment that occurs only once every 176 years. Along the way, it revealed Jupiter's swirling great red spot, Saturn's dazzling and complex rings, and became the first spacecraft to visit the enigmatic ice giants, Uranus and Neptune, opening our eyes to worlds we had only glimpsed from afar. At Uranus, Voyager 2 discovered a planet tipped dramatically on its side, spinning almost perpendicular to the plane of the solar system. It found faint rings, a magnetic field unlike any other, and moons with mysterious icy surfaces. At Neptune, the spacecraft unveiled supersonic winds, the fastest in the solar system, and a mysterious great dark spot, a storm as large as Earth. It also captured haunting images of Triton, Neptune's largest moon, with geysers erupting from its frozen surface. With its planetary mission complete, Voyager 2's journey was far from over. It set its sights on a new, even more ambitious goal: to become humanity's first messenger to the stars, embarking on an interstellar mission. Leaving the familiar planets behind, Voyager 2 ventured into the vast, uncharted territory beyond the sun's influence, aiming to cross the final frontier of our solar system, a journey into the unknown that would take decades. For years it traveled through a seemingly empty expanse, still cocooned within the solar wind's protective bubble, known as the Heliosphere. This invisible shield, created by the sun, marks the boundary between our solar neighborhood and the interstellar medium. Voyager 2's new mission was to reach the very edge of this bubble, to become the first to cross into true interstellar space and sample the material between the stars. The distances involved are almost impossible to grasp, billions of kilometers from home, with signals taking more than 16 hours to reach Earth. Yet Voyager 2 persisted, faithfully sending back data from the darkness. It was tasked with answering one of the most profound questions in space science: what lies at the very edge of the sun's influence, where our star's power finally gives way to the galaxy beyond. Voyager 2's ultimate purpose was to travel to the edge of this cosmic bubble and, if it survived long enough, to punch through it, becoming a silent pioneer in the great unknown of interstellar space, carrying humanity's message to the stars. Imagine our solar system as a vast bubble, the heliosphere, a protective shield inflated by the solar wind. This solar wind, a stream of charged particles, constantly flows outward from the sun, creating and maintaining this bubble. Traveling at over 1,000,000 miles per hour, these particles push against the interstellar medium, the matter that exists in the space between stars. But the sun's influence, though vast, cannot extend forever. As the solar wind travels further from the sun, it begins to lose its strength. Far beyond the most distant planet, the solar wind weakens significantly, meeting the inward pressure of the galaxy. This boundary, where the solar wind's strength is finally balanced by the interstellar medium, is known as the Heliopause. It marks the outermost edge of our solar system. For Voyager 2, this journey involved crossing the termination shock in 2007, a region where the solar wind dramatically slows down and becomes more turbulent. Beyond this point lies the heliosheath, a turbulent region where the solar wind piles up against the heliopause, creating a chaotic environment. Voyager 2 spent over a decade traversing this chaotic region, measuring strange and unexpected conditions that challenged our understanding of space. On November 5, 2018, Voyager 2 registered a sudden drop in solar wind particles, a clear sign that it was approaching a significant boundary. Simultaneously, there was an increase in cosmic rays, high-energy particles from outside our solar system, indicating that Voyager 2 was entering a new region of space. The message was clear. Voyager 2 had crossed the heliopause, leaving the protective bubble of the heliosphere. It had left the sun's cradle and entered the vast, uncharted territory of the interstellar medium. Voyager 2 was now flying through the stuff of the stars, a region filled with mysteries and new discoveries waiting to be made. This wasn't just a line on a map, it was a dynamic transition zone holding secrets of our solar system's interaction with the Milky Way galaxy. Voyager 2 had crossed the Heliopause, leaving the sun's cradle and entering the interstellar medium, embarking on a journey through the unknown. Before the Voyager missions, our understanding of the Heliopause, the outermost edge of our solar system, was based almost entirely on theory and mathematical models. Scientists had never observed this distant frontier directly, so much of what we believed was built on educated guesses and indirect evidence. We pictured the Heliopause as a clean, almost pristine boundary, where the solar wind from our sun would abruptly collide with the interstellar medium, the vast cold expanse between stars. It was imagined as a sharp dividing line, almost like a cosmic border checkpoint. The transition was expected to be sudden and unmistakable, like stepping from a warm, sunlit room into the chill of night air. We thought the change would be obvious, with clear signs marking the crossing. We also anticipated a dramatic shift in magnetic fields as the probes crossed this boundary. Instruments on board would, we believed, register a clear and sudden change, confirming the moment of entry into interstellar space. The region just inside the heliopause, known as the heliosheath, was thought to be hot and turbulent, while the interstellar medium beyond was expected to be cooler and calmer, a stark contrast between two cosmic environments. But when Voyager 1 crossed the heliopause in 2012, the data it sent back hinted that our models were far too simple. The transition was not as clear-cut as we had imagined. Voyager 2's crossing years later shattered our expectations even further. Instead of a neat boundary, it revealed a region far more complex, filled with turbulence and unexpected phenomena. The heliopause turned out to be not a simple static line but a dynamic and ever-changing region, shaped by forces we hadn't fully understood. It was a place of constant motion, where solar and interstellar winds tangled in unpredictable ways. Our predictions had painted a tidy, almost textbook picture of the solar system's edge. But reality, as revealed by the Voyagers, proved to be far more intricate, challenging everything we thought we knew. Voyager 2's data showed us a boundary that was not only more complex and dynamic than we had ever imagined, but also a reminder of how much there is still to discover at the very edge of our solar system. Voyager 2's crossing revealed startling temperatures at the heliopause. The plasma was hotter than expected, reaching up to 50,000 Kelvin. This superheated gas was a surprise, prompting new theories. The spacecraft survived due to the low density of particles, transferring little heat. The heat is generated by interactions between solar wind and interstellar hydrogen. Neutral hydrogen atoms become charged ions, accelerating and heating the plasma. This discovery redefined our view of the solar system's boundary. The heliopause is a dynamic interface, a natural particle accelerator. Voyager 2 provided direct evidence of this energetic frontier. Voyager 2 uncovered a magnetic puzzle at the heliopause. Scientists expected different magnetic orientations inside and outside the heliosphere. Voyager 1 found the fields aligned, initially dismissed as a coincidence. Voyager 2 confirmed this alignment, suggesting a genuine feature. The interstellar magnetic field drapes around the heliosphere, shaping its structure. This discovery highlights the magnetic boundary's complexity. The heliopause is a magnetic handshake, a feature no one predicted. Even beyond the heliopause, the sun's influence lingers. The heliopause is not an absolute border. The sun's reach extends beyond. Voyager 1 detected unexpected increases in plasma density and pressure. These events are linked to solar flares crossing the heliopause. The boundary is porous, dynamic and influenced by the sun's activity. The sun's influence complicates the picture of interstellar space. The heliopause is a transition zone, not a simple line. The sun's presence is still felt, a reminder of the star system left behind. The Voyagers revealed a complex, messy boundary where the sun's influence lingers. The heliosphere's shape remains a mystery. The comet model suggested a long tail, but new theories propose a croissant shape. The Voyagers provide data from only 2 points, limiting our understanding. More data is needed to map the heliosphere's global structure. The Voyagers replaced a simple picture with a complex mystery. Solving this mystery requires a new generation of explorers. As of 2025, both Voyagers continue their interstellar journey. Voyager 1 is over 15 billion miles from Earth, Voyager 2 over 13 billion. Communication is a whisper from the past, a testament to engineering. The probe's power sources, RTGs, are dwindling, requiring careful management. NASA is shutting down non-essential systems to conserve power. The goal is to keep at least one instrument operating into the 2030s. Despite challenges, the mission continues, pushing the boundaries of knowledge. Incidents remind us of the fragile connection across the solar system. The Voyagers still report on interstellar conditions, feeling the sun's shockwaves. They continue to expand human knowledge with every mile traveled. The Voyagers opened a new chapter in exploration, raising more questions. New Horizons is the next spacecraft to cross the Heliopause, expected in the 2030s. The Interstellar Mapping and Acceleration Probe, IMAP, will map the heliosphere. IMAP will provide a comprehensive view, turning Voyager data into a complete picture. Future missions may explore the outer heliosphere and interstellar medium. The Voyager's journey is a testament to human curiosity and ambition. They carry a golden record, a message to the cosmos. Their legacy is the knowledge they sent back, changing our sense of place. The Voyagers taught us our home is bigger and more wonderful than imagined. They are silent monuments to human ingenuity, drifting through the Milky Way.